use case, product recommendations on a shopping site. Let's say you've been tasked with creating the back-end application that will provide product recommendations to customers based on their past purchases. Classical programming is traditionally how these needs were handled in the past. Programmers would set up rules that said, if this customer purchased product X in the past, show them product Y, because there was some established relationship between these two products. While this can occasionally prompt customers to make that second purchase, it required programmers to explicitly define and set these rules. They couldn't take very much additional context about the customer or the products into account. In addition, customers are unique, and just because one customer was interested in products X and Y doesn't mean that most or even many customers will be interested in the same products as well. Machine learning, by contrast, would let us use a variety of data collected in the past to automatically derive the patterns hidden in that data. The patterns are then used to create the model, which is applied to new data to provide a more well-informed and adaptive prediction. In this example, we'll be able to use the customer's purchase history in combination with the data of customers and sales site-wide. We can use machine learning to identify the patterns between past customers and sales, and then apply those patterns to new customers in order to provide better recommendations to them. So what is a model exactly? A model in machine learning is the trained algorithm you use to identify patterns in your data. The key there is that it's trained through the machine learning process. It isn't created manually by programmers setting up rules like in classical programming. Let's look at a very simple example algorithm. Here's an example algorithm. This has been simplified from what you might use in a real environment, but it shows what are the two key components of an algorithm: features and weights. Features are the parts of your data set that are identified as important in determining accurate outcomes. For example, with our product recommendation algorithm, the first feature might be whether or not the item is a hat. These features have to be expressed mathematically, so in this case, our model will convert a yes into a 1 and a no into a 0. But key to machine learning is the idea of context. That's where weights come in. Weights represent how important an associated feature is to determining the accuracy of the outcome. So something that has a higher likelihood of accuracy has a higher weight, and vice versa. In this case, our model has been trained and has determined that because this customer has purchased 8 hats in the past, that translates to a weight of 0.8. It's important to note that this is a very simplified version of what really goes on, but for now, this is the most crucial part of understanding how weights and features work in an algorithm. Let's look at the next set. The second feature has to do with whether or not a product is from a particular brand. The product is from that brand, so that converts again to a 1. The second weight says that since 2 out of the 8 items this person bought in the past were from that brand, that results in a weight of 0.25. If this was a very simple model, this is what you'd end up with. Let's say the standard for whether or not to recommend is if the final value is greater than 1. The model performs this calculation and finds the final value to be 1.05. Therefore, this product is an acceptable recommendation. Let's get back to the different types of machine learning algorithms. There's supervised learning, where a model uses known inputs and outputs to generalize future outputs. There's unsupervised learning, where the model doesn't know inputs or outputs, so it finds patterns in the data without help. There's reinforcement learning, where the model interacts with its environment and learns to take actions that will maximize rewards. And then there's deep learning, which is a subset of machine learning. These algorithms learn by using artificial neural networks. Again, it's important to know the types of machine learning because the type will guide you towards selecting an algorithm that makes sense for solving your business problem. First, let's talk about supervised machine learning. Supervised learning is a popular type of machine learning because it's widely applicable. It's called supervised learning because there needs to be a supervisor, a teacher, who can show the right answer, so to speak. Like any student, a supervised algorithm needs to learn by example. Essentially, it needs a teacher who uses trained data to help it determine the patterns and relationships between the inputs and outputs. Here, in this picture, is a car. Here is a car in another picture. The model is trained on this label data so that it can accurately identify where a car is in a new picture it hasn't seen before. But within supervised learning, you can have different types of problems. These can be broadly categorized into two categories: classification and regression. Think of machine learning problems falling into one of two categories: classification and regression. With classification problems, there are actually two types. The first is considered a binary classification problem. The target value in this example is limited to only two options. This is an example of a binary classification problem that you're classifying an observation into one of two categories. There are also multi-class classification problems. These machine learning problems classify an observation into one of three or more categories. Pretend you have a machine learning model that predicts why a customer is calling your store so that you can reduce the number of transfers needed before getting the customer to the right customer support department. The different customer support departments, in this case, represent the variety of potential target values, which, needless to say, could be many different departments, far greater than two. There are also regression problems. In a regression problem, you're no longer mapping an input to a defined number of categories, but instead to a continuous value, like an integer. One example of a machine learning regression problem is predicting the price of a company's stock. For example, here a regression-based algorithm is predicting that tomorrow the stock price for a company will be from $113 per share to $127 per share. Now, let's talk about unsupervised machine learning. Sometimes all we've got is the data. There's no supervisor in the room. In unsupervised learning, labels are not provided like they are with supervised learning. We don't know all the variables and patterns. In these instances, the machine has to uncover and create the labels itself. These models use the data that they're presented with to detect emerging properties of the entire data set and then construct patterns. A common subcategory of unsupervised learning is called clustering. This kind of algorithm groups data into different clusters based on similar features in order to better understand the attributes of a specific cluster. For example, by analyzing customer purchasing habits, unsupervised algorithms are capable of identifying groups of customers that identify a particular company as being large or small. It may be sufficient for smaller companies to purchase basic cloud hosting resources, while larger companies may be more likely to purchase entire cloud solutions including advanced security, dedicated private connections, virtual private clouds, and more. Clustering in this situation may help you to realize that you need to come up with a different marketing strategy for different sized companies. The advantage of unsupervised algorithms is that they enable you to see patterns in the data that you were otherwise unaware of, like the existence of two major customer types. One use case for unsupervised learning is anomaly detection, such as the speed camera example here. This model is designed to detect potential hardware failures of speed cameras by looking for anomalies in the data. In a classical programming solution, every data point outside of a clearly defined boundary would have to be evaluated as a potential failure. But with unsupervised learning, models can identify what are simple outliers, such as people driving at a very high rate of speed at random points during the day, and what's more likely to be a result of hardware failure, a high volume of extremely high speeds recorded over a span of time. Now let's talk about reinforcement learning. Take the example of AWS Deep Racer as shown here on the slide. In the AWS Deep Racer simulator, the agent is the virtual car. The environment is a virtual racetrack. The actions are throttle and steering inputs to the car, and the goal is completing the racetrack as quickly as possible and without deviating from the track. The car needs to learn the desired driving behavior to reach our goal of completing the track. To learn this, we will use rewards to incentivize our model to learn the desired driving behavior. In reinforcement learning, the thing driving the learning is called the agent. In this case, it's the deep racer car. The environment is the place where the agent learns, which in this example would be the marked racetrack. When the agent does something in the environment that provokes a response, such as crossing a boundary it shouldn't cross, that's called an action. Now, the response to that action is a reward or penalty depending on whether the agent did something to be reinforced or discouraged in the model. As the agent moves within the environment, its actions should start receiving more and more rewards and fewer penalties until it meets the desired business outcome. So what is deep learning? Now that we've talked about the three categories of machine learning, let's talk a little bit about specifically deep learning. Deep learning is a subset of machine learning. These algorithms learn using artificial neural networks, so let's dig into that a bit. Deep learning represents a huge leap forward in the capabilities for artificial intelligence and machine learning. While the theory for deep learning goes back decades, the hardware required to run deep learning problems wasn't generally accessible until very recently. But now that it's available, we're able to use deep learning to address problems more complex than we could before. To demonstrate the leaps between these three categories, we can use the classic example of machines that play chess. With classic artificial intelligence, the machine couldn't learn anything that wasn't given to them directly in the code. So a machine could play chess based on rules that were provided, but any improvements to its strategy would have to come from a programmer explicitly calling them out and programming them in. With machine learning, chess-playing machines can actually learn and improve their chess skills by doing things like analyzing past chess games that were played by humans. They could be provided with simple chess strategies, but then use something like traditional reinforcement learning where they can identify patterns and moves that were more likely to result in winning versus moves that were more likely to result in losing the game to hone their performance. But now, with deep learning, we're able to create machines that can learn chess in a fashion more like how humans learn it, by playing. A deep learning machine could be given the most basic rules on how chess is played and use its complex layer-based iterative approach to learn its own chess strategies and recognize patterns several orders of magnitude more complex than a traditional machine learning model could. The deep learning models in use today rely on things called artificial neurons. These are math functions that can receive inputs and sum them up to create an output. Work on artificial neural networks began back in the 40s. However, it wasn't until technological breakthroughs in the 2010s enabled artificial neural networks to be used in real environments. In an artificial neural network, each layer summarizes and feeds information to the next layer, ultimately producing a final output or prediction. During this process, the model derives the features itself. We've talked about features, their importance, and how they're used in classical programming. Let's look at how the use of features evolved from classical programming to machine learning to deep learning. As we've established before, in machine learning, the features are manually engineered and then used to train and develop the model. But in deep learning, the features are derived by the artificial neural network itself during the training and tuning process. The performance of the model based on that training is then fed back in through the artificial neural network iteratively until generating the final model. Let's break this down into a more concrete example of a deep learning analysis of an image. In this example, we see that the machine starts by identifying specific features of the input beginning with pixels. From there, it identifies edges, corners, contours, and object parts before making a prediction as to what the object is. In this way, it is extracting features like edges, corners, and parts automatically based on the algorithm and the data it's being trained on. It can identify patterns at levels that the human eye can't easily identify. Again, the premises for deep learning started in the early 20th century, but the impact of improvements made in the field was really felt in the early 2000s. The big shift began with the ImageNet Large-Scale Visual Recognition Challenge, which is a competition where research teams submitted programs that classified and detected objects and scenes in photographs. In 2010, the first year of the challenge, the winner of the challenge had a model with an accuracy rate of 71.81%. In 2011, the accuracy marginally improved to around 74%. In 2012, when deep convolutional neural networks, common in deep learning models, started to be used, the accuracy rate jumped up to about 82%. Then, in 2015, the winning program actually exceeded human performance at these computer vision tasks. Now, let's explore the machine learning pipeline by walking you through its different steps. So to begin, you should always start with the business problem you or your team believe could benefit from machine learning. From there, you want to do some problem formulation. This phase entails, in part, articulating your business problem and converting it to a machine learning problem. After you've formulated the problem, you move on to the data preparation and pre-processing phase. Data preparation and pre-processing includes the following: data collection and integration in order to ensure your raw data is in one central accessible place, data pre-processing and data visualization, which includes transforming raw data into an understandable format and extracting important features from the data. All this is done to ensure your data is formatted correctly for your machine learning algorithm and that your data is cleaned up in a way that will maximize your model's prediction power. Once these steps are complete, you're ready to train and tune your model. This is an iterative process that can be performed many different times throughout this workflow. Initially, upon training, your model will not yield the results you may be expecting. Therefore, you will perform additional feature engineering and tune your model's hyperparameters before retraining. This cycle is repeated until your model's evaluation shows it is performing at the level required by your business case. If your model doesn't meet your business goals, you will need to go back and reevaluate a few things. Take a second look at your data and features for ways to improve the model and the way that it's produced. Building a model usually is an iterative process in this way. Once the retraining happens and you're satisfied with the results, your model is deployed to deliver the best possible predictions, which is often a tedious and manual effort. By reviewing the steps of the pipeline and mapping them to the correct machine learning services, you can simplify and automate this overall process to create robust machine learning models. The Amazon call center problem. Several years ago, Amazon needed to improve the way it routed customer service calls, so it looked to machine learning for help. The original routing system worked something like this. A customer would call in and was greeted by a menu. Press 1 for returns, press 2 for Kindle, press 3 for, well, you get the idea. The customer would then make a selection and be sent to an agent who would be trained in the right skills to help the customer. During the problem formulation phase of the pipeline, Amazon determined that the current routing system was problematic. Thinking about Amazon, you may be able to guess that we do sell a lot of stuff here, and so the list of things a customer might be calling us for is, well, just about endless. So if we didn't play the right option to a customer calling in, the customer might be sent to a generalist or even the wrong specialist who then had to figure out what the customer needed before finally sending them to the agent with the right skills. For some businesses, maybe that's not the end of the world. For Amazon, dealing with hundreds of millions of customer calls a year, it was pretty inefficient. It cost a lot of money, wasted a lot of time, and worst of all, it was not a good way to get our customers the help they needed. So the business problem that was articulated at this phase was focused around figuring out how to route customers to agents with the right skills and therefore reduce call transfers. To solve this problem, we needed to predict what skill would solve a customer call. Converting to a machine learning problem, this became identifying patterns in customer data that we could use to predict accurate customer routing. Based on the wording of this machine learning problem, it was clear that we were dealing with a multi-class classification problem. Since we wanted to base our predictions on past data from customer service calls, we were dealing with supervised learning. We eventually would train our model on a bunch of historical customer data that included the correct labels or customer agent skills. That enabled the model to make its own predictions on other similar data moving forward, predicting, say, that a customer call needed a Kindle skill. The data we needed for this came from answering questions like, what were customers' recent orders? Did customers own a Kindle? Were they Prime members? The answers to these questions became our features. We then moved on to the data preparation or pre-processing phase. This phase includes data cleansing and exploratory data analysis. Now, a lot was done at this point, but one example of data analysis undertaken was to think critically about the labels we were using. We asked ourselves, are there any labels that we want to exclude from the model for some reason? Are there any labels that are not entirely accurate? Any labels similar enough to be combined? Finding answers to some of these questions by exploring the data would help cut down on the amount of features being used and simplify our model. An example of what may be found in this type of analysis was, instead of having labels represent multiple Kindle skills, it made more sense to combine these skills into one overarching Kindle skill label, so that every customer who had a problem with a Kindle was routed to an agent trained in all Kindle issues. Data visualization was the next step, where we did a number of things, including a programmatic analysis to give us a quick sense of feature and label summaries, effectively helping us better understand the data we were working with. At this point, we may have noticed that 40% of calls were related to returns, 30% were related to Prime membership, 30% were related to Kindle, and so on. Important information that gives us a better sense of the data we were working with. We then moved on to feature engineering. We had some features that answered questions like, what was a customer's most recent order? What was the time a customer's most recent order came in? And did customers own a Kindle? When we feed these features into the model training algorithm, it can only learn from exactly what we show it. Here, for instance, we are showing the model that this purchase was made at 1 p.m. on Tuesday the 13th. Unless we want to predict something really specific, or we're doing a time series analysis, that might not be the most meaningful feature to feed into our model. It would be more meaningful if we could transform that timestamp into a feature that represents how long ago that order took place. Knowing, for example, that your last purchase was months ago will probably help the model realize that your last purchase probably isn't related to the reason you're calling. Obviously, we can engineer this feature by just taking the difference between the order date and time and today's date and time. Now that's a much more useful feature. A big part of preparing for that training process is to first split your data to ensure a proper division between your training and evaluation efforts. Think about it this way. The fundamental goal of machine learning is to generalize beyond the data instances used to train models. You want to evaluate your model to estimate the quality of its predictions for data the model has not been trained on. However, as is the case in supervised learning, because future instances have unknown target values and you cannot check the accuracy of your predictions for future instances now, you need to use some of the data that you already know the answer for as a proxy for future data. Evaluating the model with the same data that was used for training is not useful because it rewards models that can remember the training data as opposed to generalizing from it. A common strategy is to split all available label data into training, validation, and testing subsets, usually with a ratio of 80, 10, and 10, or another common ratio is 70, 15, 15. After running a training job, we evaluated our model and began a process of iterative tweaks to the model and our data. For instance, we performed hyperparameter optimization. We tweaked the learning parameters to control how fast or slow our model was learning. Learning too fast means that the algorithm will never reach an optimum value, while learning too slow means that the algorithm takes too long and may never converge to the optimum in the given number of steps. Once happy with how the model interacted with the unseen test data, we deployed the model into production and monitored it to make sure that our business problem was indeed being addressed. Our problem was predicated on the assumption that the ability to more accurately predict skills would reduce the numbers of transfers a customer experienced. That was put to the test after we deployed, and in fact, the number of transfers did decrease, resulting in a much better customer experience. We then deployed the model, and it now helps customers get directed to the correct